Hey everybody, Megan here. So we've been looking at derivatives in physics and seeing how the instantaneous rate of change of any function can be found at any moment in time. We found that to be incredibly important as we were learning about how to take a position function and change it into a velocity function because we said, hey, the instantaneous rate of change of position is velocity. And so we learned to take the derivative ddt of the position function with respect to time, and that finds the velocity function. Similarly, we saw that the velocity function, the instantaneous rate of change of the velocity function at any moment in time, meaning the derivative of the velocity function at any moment in time, is the acceleration function. So it kind of feels like, shouldn't there be a way to go backwards? And of course there is. And so today's lesson is all about the antiderivatives. So antiderivatives in physics. Antiderivatives are the opposite, the inverse, the undoing of a derivative. Another word for an antiderivative is an integral. And so to just like how we did not do a good job according to your math teachers, because we did not actually teach you how or why derivatives make sense. We did not really go into the limit definition of things. We're leaving that up to your math teachers. We also are going to do a quick and dirty, like how to take an integral and showing you what they mean, how to take an antiderivative, and how we're going to use those in physics, but not really do a good job of showing you how and why. Sorry, we're going to leave that all to the math teachers. But just know that the goal of an antiderivative, so like Newton and Leibniz, they were chilling in the 1600s, figuring out, like really thinking closely about rates of change of functions. But they realized actually, like, if the position function has an instantaneous rate of change that is velocity, there is something that's happening over time, right? As like the position of that object is changing as, like at a certain rate. And that thing that's happening is that position is almost, or displacement is accumulating as this object moves through time. And so they realized that an antiderivative, the inverse of a derivative, and I know your math teacher's gonna be like, Megan said this way weird and way wrong, but this is how physicists think about it, and this is how Newton was thinking about it. He was thinking of antiderivatives as almost like the accumulation of change. And he wasn't saying it over a specific moment in time, like we were talking about with the derivatives, but the change over a time interval. And so that's actually what we're doing when we go backwards from a velocity function to a position, or showing the change in position over time, aka the displacement. When we take the integral, or the antiderivative of velocity, we're seeing how much did the position change during a certain amount of time, or from one time to a different time. And same thing with acceleration to velocity, showing if acceleration is changing over a certain amount of time, how did that accumulate a change in velocity? And then you can almost imagine like going from acceleration to velocity, showing the accumulation of change in velocity, and that then going backward and thinking about how much did my change in position or my displacement accumulate over time. And so that's really what an antiderivative is, and that's how we're going to teach today. So let me show you a super basic example, something really, really dumb. For example, here's an object that has a velocity time graph like you see here. So we've got a velocity function that says, hey, this object is always moving at a constant velocity of 2 meters per second. So this is so simple, we could absolutely figure out how far that object's gone or what its position is over time. Actually, you'll remember that this velocity graph shows you nothing about where this thing starts. We actually have no idea where it starts. No idea. So I'm just going to make something up. Let's pretend this starts at a position of 1 meter. And then let's think about, well, over that 1 second of time that happened, how far did it go? Well, if it's going 2 meters per second, in the first second it goes 2 meters. And so we know that if it starts at 1, goes 2 meters, it ends up at 3. Again, in the second moment of time, it's still going 2 meters per second. So it goes another 2 meters in that 1 second of time, and so it ends up at 5 meters. Another 2 meters, it ends up at 7, another 2 meters, it ends up at 9. Okay, you get it. So this is a really, really simple function that says, hey, I go 2 meters per second every second. So I'm wondering, or this is really what Newton was wondering, is could we show this accumulation of distance somehow graphically using this velocity time graph? And so I think somebody actually mentioned this the original day. We actually see the accumulation of distance, or the change in position, aka the displacement, as the area under this curve. One more time. If I look at this little rectangle here that was made in the first 1 second of time, I notice that the base of this rectangle, I'm going to put this in a different color, make this really big. So the base of this rectangle is 1 second of time. The height of this triangle is the velocity it's going, aka 2 meters per second. And so the area of this rectangle is 1 times 2 gives us 2. 2 is the delta x, the displacement. But it actually works if we continue looking at what happens over the first 2 seconds of time. So if we look at the area of the area under the curve, aka the accumulation of position over this entire 2 second time interval, we see, oh, now we've got a base of 2 seconds, we've got a height of 2 meters per second, and if we multiply and find the area, again, what we're doing here is we're multiplying v times t, and v times t is displacement. Why? Because that comes from v average equals distance over time. Sorry, v average equals displacement over time. I can like hear Mr. Brown in my head being like, oh, it's smart. Okay, so we know that the average velocity, which of course, because we're at constant velocity, is the same as this velocity, times time multiplied by time gives you the displacement. The area under this curve is the displacement. And we can see that a height of 2, a base of 2 gives me 4 meters. I have moved 4 meters from where I started, but remember where I started was 1, and so over this 2 second time interval, I've moved a total of 4 meters, and so my displacement is 5. Does it keep working? Sure it does, because if I go to 3 seconds, now I've accumulated, well, 2 meters per second times 3 seconds gives me 6, and so from my starting position of 1, I change by 6 meters, and so I get to a total position of 7 meters. And so here's the key thing here, my friends, is that this area under the curve, so the area under the curve of a velocity time graph gives you the displacement. Displacement being like delta x. Did it give you the actual position of the object? No. You still needed to know where the object started. We needed to know that it started up here at x equals 1 to be able to know that it's traveled this much displacement, and therefore where is it now? So this is really just a clever way of using the area under the curve. So, of course, that's a really simple function. That's a function where we had a constant velocity. What happens when we have an acceleration, a changing velocity? Okay, let's do a second example, a little trickier this time. So instead of an object moving with constant velocity, let's imagine something that has changing velocity. So it says this object moves with a velocity function, v of t equals 3t. Okay, so I could like quickly map out what that looks like. At t equals 0, my object would have 0 velocity. At t equals 1, my object would have 3 meters per second of velocity. T equals 2, 6 meters per second. So I can see that this number 3 is the slope of this line. You might even remember, right, the slope of a velocity time graph, that's the acceleration. So it is changing at a rate of 3 meters per second every second. So we could take the derivative or the slope of this line to figure out the acceleration, but I want to do the opposite. I want to know how far has it gone. And I'm going to make this a little trickier. I actually only care about how far did it go from t equals 1 to t equals 2. So not in the first moment of time. Pretend I don't care about that. I just care about like how far did it go from time 1 to time 2. Only in that second. So it has accumulated distance. How much has it accumulated? Aha, Megan, you already are saying to me, well, I know that the area under this curve from 1 to 2 looks like this. And maybe you've even noticed, actually, we could split that into some regular pieces. We could figure out what this rectangle is, and we could figure the area of that rectangle, which would tell me how far it went if this was a constant velocity of 3 meters per second for 1 second. So of course we'll go 3 meters. And add that to the triangle at the top here, which is how far it would go if I moved for 1 second from 3 to 6 meters per second. So I changed by 3 meters per second every second, times a half because it's a triangle, so 1/2 base times height. And I would get something like 1/2 the base, which is 1 second, right, because from 1 to 2, times the height, which is changing by 3 meters per second. So that gives me 3/2 meters, plus this one, right, a height of 3, a base of 1, so 3 meters for here. And so I could say, oh, the displacement from time 1 to time 2, this is not the right way to write this, but I'm going to do it anyway. From time 1 to time 2, what is the displacement? Well, it's 3/2 plus 3, so 4.5 meters. Okay, so that's one way to do this problem. And it's a simple way. Let me show you a different way to do this problem, which is maybe a little clever. You could have been like, well, I could figure out the bigger triangle and subtract this smaller triangle out of it. Then the displacement here would also be hopefully 4.5, but let's double check that that works using, again, the purple bigger triangle from 0 to 2 seconds minus that smaller triangle. And so this is really what Leibniz was, or Newton and Leibniz were kind of like thinking about at the time, is like, how can we do this graphically using this accumulation, this area under the curve? So how would we do it? We'd say, all right, well, the displacement of the purple triangle, that's 1/2 base of 2, height of 6, right, from 0 to 6, minus the red triangle displacement, which was from 0 to 1, so 1/2 the base, which was 1, times the height, which is 3. Okay, so 1/2 the base times height, that's 3/2. 1/2 2 times 6 gives me 6. And so the total distance in sort of like black, just from 1 to 2, to match with what we had before, should be, I'll subtract, so from 1 to 2 gives us 6 minus 3/2. 6 minus 1.5 is 4.5, just like we expect. Okay, so again, that's not very clever. That's not different. Neither of these two approaches is better than the other one. But this second one leads us to the integral, and so the antiderivative. So let me show you how to use a similar purple minus red approach using the integral. So we have the velocity of time function. We know the velocity of time function is 3t. The way that we write the integral notation is we write this little S thing. I forget what this stands for. It basically means sum of. So it's kind of like that summation symbol in math class, but like if you write it enough times, it kind of just becomes an S, whatever. It basically means summing up many, many, many little pieces. And I'll show you in a minute what those many little pieces are in Newton's mind. So essentially we write this little thing. We say what time we're starting at the bottom, what time we're ending at the top. And then we just, for a reason that your math teachers are going to explain, we write dt. So that just means that we're integrating with respect to time. We're integrating the velocity function with respect to time. Okay, so that's what the antiderivative means. And again, that does mean we're just finding the accumulation. We're finding the area under the curve. And so let's show how to do that. So I'm just like writing my notation again. I'm going to plug in my v of t function. So my v of t function was 3t. I'm just writing that dt. Okay, well, how do I find the inverse of a derivative? So essentially, so this is my like side note over here. So essentially what I'm trying to say is, all right, so what the derivative with respect to time of what would give me 3t? Because I know that the derivative with respect to time of the position function would give me a velocity function of 3t. And so we have to kind of like think about, well, what did I do to get the derivative, right? So when I take a derivative, I always take the exponent. I bring the exponent down and multiply that out front. Then the exponent decreases by 1. So to undo that, the exponent needs to decrease, not decrease by 1, but increase by 1. So if my new exponent is 3t to the first, that means that my original exponent over here had to be t to the second, t squared. Because if it was decreased by 1 to get to 3t. So I undid that. Secondly, that 2, when I took the derivative, would have been multiplied through out front. So to undo that, instead of multiplying by 2, I would divide by 2. So one more time, let's double check that this works. So this is what I have right now, and I am going to do something in a minute where I like show you how to evaluate that from time 1 to time 2. But essentially what we did here was we said, all right, so what function would I have to take the derivative of to get 3t to the first? So one more time, what function would I have to take the derivative of to get 3t to the first? Well, if I took the derivative of 3/2 t squared, then by using the power rule, the 2 exponent would come and multiply by the 3/2. Those 2's would cancel and I'd be left with a coefficient of 3. Then my exponent number would decrease by 1, so 2 minus 1 would give me t to the first. And so this would be 3t to the first. So therefore, the antiderivative of 3t to the first is 3/2 t squared. I'll put some extra reading if people want to sort of follow that. Okay, so then we say, all right, well, the integral, the indefinite integral, don't worry about this language, of this function is 3/2 t squared. So therefore, the displacement, 3/2 t squared. But I know that I don't care about that from any moment in time to any moment in time. I care about it from time equals 1 to time equals 2. And so we, to keep track of the fact that I haven't yet dealt with that, I put a little line over here, which is sort of looks like the little squirrely s integral, but it isn't. And it says, let's evaluate that from time equals 2 to time equals 1. And what we do is we plug in a difference. So we say, all right, well, the displacement is the final, so 3/2 time equals 2 squared minus the initial 3/2 of time equals 1, 1 squared. So I'm taking this notation where I'm saying the displacement is 3/2 t squared for any moments in time, and I'm saying, let's evaluate that from the final time 2 back to the initial time 1. So final minus initial of that function gives me a delta x of 3/2 times 2 squared. 2 squared is 4. 4 times 3 is 12. 12 over 2 is 6. Minus 1 squared is 1. 1 times 3/2 is 3/2. And so I get 6 minus 3/2 is 4.5. In fact, check this out. I did the exact same operation, 6 minus 3/2 up here. One more time. I did that exact operation here. So essentially, this part of my definite integral, 3/2 2 squared, is the exact same thing, that like value of 6, that's the same thing as that triangle, the triangle from t equals 0 to t equals 2. And I subtracted 3/2, 1 squared, which was the same thing as this triangle, that red triangle there. And so it's the exact same approach is saying like, so add up all the values, all the area under the curve from 0 to 2, subtract all of what was 0 to 1, and then what I have left over is from time 1 to time 2, the actual displacement. Quick note to yourself, is this where the object is? No, because we have no idea where this object starts. And so we only know how far it's gone from where it started to where it ended. So in math class, you're going to learn to write a plus c constant here because you don't actually know where it starts. I like to, in physics class, write this as, so I'm going to turn this into delta x, the function, delta x or delta x of t, equals 3/2 t squared plus a constant. We know that constant represents where we've started, so I just call it x naught. So really what this thing has done is it's given us a position function as a function of time that says 3/2 t squared plus wherever I started. And so this would be a nice physicsy way to write this function. All right, team. None of this is the real reason why calculus exists. The real reason why calculus exists is for functions like this, where the velocity changes not constantly, not using uniform acceleration, but in some new funky way over time. All right, so we've seen two examples. What's the rule? What's the rule of taking the antiderivative, again, just for polynomial functions? So this undoes the power rule. So we said, all right, if we've got some f prime of x, some derivative, then we know that, let's make up a function. So we say f prime of x, the derivative of something is ax to the n power. Okay, so then the integral of that, so f of x, which is of course the integral of f prime of x from some lower value, let's call it a, to some upper value, let's call it b, with respect to x. So the derivative, the integral of f prime of x, the integral of the derivative with respect to x, is equal to, okay, let's see. So we've got from a to b of ax to the n power dx. What do? We add 1 to the exponent, x to the n plus 1, and then we had to divide, instead of multiply, by that new exponent, n plus 1. And then we evaluate all of that from x equals a, I should probably write x equals a, to x equals b. Of course, in physics, we often didn't use the x variable, we used time as our variable. And so from a time a to time b with respect to t, this is it. So when we evaluate this, we do a b to the n plus 1 over n plus 1 minus a to the n plus 1 all over n plus 1. And don't forget that all of this shows us an f of x function that has no idea where it started. And so in calculus, you'll always add a plus constant, and that constant is meaningful in physics. So quick reminder that we were looking how to go from a position function to a velocity function by taking the derivative with respect to time. And so to undo that, we had to take the integral of the velocity function with respect to time to get the position function plus the initial position. To take the velocity function and go to the acceleration function, we take the derivative with respect to time, so d dt of velocity gave us acceleration. To undo an acceleration function, we take the integral of a of t with respect to time, and then, what's the constant that we add on to that? So if to find the position function, we need to know the initial position. To find the velocity function from the acceleration, we need to know the, hope you got it, initial velocity. So that's the constant that we add. Try this problem. If a of t, try this. If a of t is equal to, let's see something with non-constant acceleration, because now we have calculus. We don't need uniform accelerated motion anymore. Let's break away from the UAM. Let's say that your acceleration function is something crazy like 2t cubed minus 3t plus 4, just for some fun numbers. Could you take the antiderivative and solve for the velocity as a function of time? And then could you take that function and solve for the position as a function of time? There'll be an example in the textbook for tonight's reading. Good luck, everybody.